Last time in Emergent States of Matter, we were considering thermal convection. That's the problem shown here on the left, where you have a fluid that is between two plates, one of which is very hot at the bottom and one of which is colder at the top. And what happens is that the hot plate causes the fluid locally to thermally expand and therefore reduce its density. Because it's in a gravitational field, the fluid rises and or can rise. And the question is, what actually happens? Now you might say, well, if there's a small temperature difference, the heat will just conduct by the regular diffusion mechanism, and you'd be right. But once the temperature difference is high enough, then what happens is you can form a variety of patterns of fluid flow that self-organize, as shown in these sketches here on the left, depending on the geometry and the parameters and the problem of viscosity, the thermal conductivity, the expansion coefficient, and the distance between the plates. So the question we want to understand is, what are the conditions under which we get a transition to these pattern-forming states? And the way that we approached this was we wrote down the differential equations describing this problem. So here on the left, at the top, we capture the fact that the fluid density is a function of the temperature and gets lower as you raise the temperature above some reference temperature with an amount proportional to the thermal expansion coefficient. Fluid, of course, is conserved and obeys a continuity equation. And in general, F equals ma translated into fluid mechanics, as we've described in the class before, leads to the equation at the bottom, which is essentially the Navier-Stokes equations in a gravitational field. And the terms that you can see here represent on the left the nonlinearity due to advection. That's the u dot grad u term. That's the term that makes fluid mechanics so complicated. The gradient of pressure, which is just the force that's applied to the system. The density times the gravitational field, that's rho g. That's the potential energy from gravitational field. And lastly, the dissipation due to viscosity. Eta del squared u is the lowest order term that is rotationally covariant, involves the shear viscosity, and of course one could envisage higher order terms too, but for the long wavelength hydrodynamic description of this system, this is adequate. So what is our strategy? Well, our strategy was to solve these equations to find a steady state which describes the conduction of the heat without any fluid motion. And then once we found that state, which was easy to construct because the equations in steady state are very simple to solve, then one can look for the stability of the system about that. Just like what we did in phase transitions, where we looked at the order parameter psi, the V being the free energy per unit volume, assuming the system is spatially uniform. And we saw that as we go below the critical temperature, the susceptibility evaluated at the order parameter being 0 point becomes negative, as you can see with the negative curvature on the right-hand side. So now we have to ask what happens when we do stability analysis, and it turned out to be technically quite complicated. On the left-hand side there at the bottom, you can see the equations we get by linearizing the equations for the temperature, the density, the pressure, and the velocity about their steady state values, and then expanding to first order. And what our strategy was to take these equations and beat them down into a form where they would just be a function of one variable. And so I spent a lot of the lecture explaining how we do that, and in particular explaining the idea that we have different scenarios for the behavior of the system as a function of the control parameter, for example, in this case, the temperature difference between the plates, and looking at how, as the real part of the stability operator, the eigenvalue omega k, its real part becomes positive. That causes the uniform steady state to have a linear instability. And we discussed that. So now there's a lot of technical fiddling around, and eventually we were able to reduce the problem to the equations that you see at the bottom in purple, a fourth order differential equation for the component of the fluid velocity in the vertical direction. And what we discovered was that the boundary conditions for this are quite complicated. In fact, actually, what I was showing you before were the boundary conditions, not the actual equation. The actual equation is the one up at the top. Sorry about that. So when what we did was we followed Lord Rayleigh, who worked out a simplified form of the problem with the boundary conditions shown here on the left. And what we were able to show was that the smallest eigenvalue, or the smallest value of delta t, which causes one of the stability eigenvalues to have a positive real part, is given by the inequality on the left. In other words, showing you that this combination of parameters, known as the Rayleigh number, has to be bigger than a certain number, which is called the critical Rayleigh number. In this particular case, it's about 600, but when you do this in an experiment and with the correct boundary conditions, what you find is the actual value is more like 1700. So what we learned was that as I increase the temperature difference between the plates, then that creates it more likely to be to exceed the critical Rayleigh number. Similarly, if you increase the distance between the plates and you increase the thermal expansion coefficient, all of those things act to make the system more unstable, the uniform system unstable. On the other hand, if we decrease the viscosity or decrease the thermal conductivity, they will also have that same effect. In other words, increasing the viscosity stabilizes the system. And you can sort of see why. Because if I've got a blob of hot stuff rising like this, if the fluid is very viscous, it's going to exert a lot of damping on this, and so it's going to make it much harder to rise. Similarly, if the thermal conductivity is very high, then a hot blob will very quickly diffuse its heat away, and so that will also act against the idea that the fluid might then start to rise. So what we want to do next is we want to try to understand something about the patterns that we get. What is the phase diagram of these patterns, and are they stable? Now, before we get into that, I want to answer a question that the one that you asked at the end of last lecture, which is, why is it that the critical Rayleigh number has a cubic dependence on the height of the convection apparatus, the distance between the plates? And it's quite a tricky question to answer. And so here's the best that I can do to try to give you some physical understanding of where that comes from. So if you look here on the right panel now, what I've drawn here is a blob of heat, a blob of fluid that is at an elevated temperature. And what we need is that that the temperature difference between it and its surrounding fluid, which is delta T, doesn't diffuse away as that little blob rises. If it diffuses away, then that blob will simply not get to the top, and we won't have any chance to get some kind of circulating pattern like this. So the time we need to compare the motion to is the following. We need to know how long does it take for heat to diffuse in this system, and that's just given by the d squared over kappa, and tc, little tc, is the time it takes for this blob to go from the bottom plate to the top plate. Okay, so what is that time tc? Well, if we knew the velocity of the blob, then we would say that that time is just the distance that you go over the velocity. So that's very straightforward. Now, we've talked about the idea that the blob is moving at a constant velocity, and that makes sense because the fluid has a viscosity, and so apart from some initial transient, a little blob like this trying to move in the background will experience Stokes drag. It'll experience a force on it that is proportional to its velocity, and it will experience another force on it due to its buoyancy. So let's go and calculate what those two things are. So the buoyancy force upward is, of course, the force itself arises from the thermal expansion coefficient alpha times the volume of the blob. So that is alpha times rho r cubed. And then that's the density of the little blob times its temperature difference, delta T, times, of course, gravity. So that's the buoyancy force. The drag force, on the other hand, opposing that is the Stokes drag, which is proportional to the velocity. And of course, we're assuming that this thing is not turbulent, particularly when it's just above the threshold for linear instability, just above the threshold for forming a pattern. So it's going to be moving slowly. And so if I had a spherical blob with radius r, then the drag is given by a formula that's proportional to the radius of the blob, the viscosity, and the velocity. And it turns out that there's a coefficient of 6 pi that is in the front of it. So that's a classical result from fluid mechanics. And so in a steady state, those two forces have to balance. And so what you get is creating the buoyancy force with the Stokes drag. You see that the velocity that it's moving at scales in the way shown here with the radius squared of the blob. Okay, so that's that. Now we need to calculate the time it takes for the blob to go from the bottom plate to the top plate, and that's given by this formula here on the right. It goes like d over r squared and so on. Now, what we need for convection is we need that the diffusion time is much longer than the transit time of the blob. So in other words, that the heat doesn't all diffuse away. So our criterion for convection should be that it's going to be in the regime where tau diffusion is much larger than Tc, and so I get this equation here on the right. And so if I though go then and reduce that equation, what I end up with is that this quantity over here, this combination of parameters, which is dimensionless, has to be much larger than some number, in this case 6 pi, but it doesn't really matter what that number is. Now, the point about this is the blob is some kind of structure whose dimensions are basically of order the plate spacing. For example, often these convection rolls involve a sort of mushroom or plume of heat that goes all the way from the bottom plate to the top plate. And so we can think of this roughly as its scale r is set by the plate spacing, so that r squared d over here ends up turning into a d cubed over here. And so that's really the explanation for physically why we ended up with this criterion from the linear stability analysis. Okay, so that's good. So now let's move on and let's now try to understand something about the phase diagram of the system. And so the way I want to do that is I want to cover in this lecture the following topics. So I want to talk about what's called the neutral stability curve. And then I want to talk about dimensional analysis. To show you how, if we want to understand the phase diagram, we've got many parameters here: alpha, delta t, d, nu, kappa. And what we're going to see is that we can take a very complicated phase diagram and reduce it to something much simpler using dimensional analysis. And I'm going to take the opportunity to mention not just dimensional analysis, but also the ideas of what are called intermediate asymptotics of the first and second kind, the idea of complete similarity and incomplete similarity. And the idea of intermediate asymptotics. of the first and second kind. I'm not going to say a lot about them. They really relate extensively to the normalization group, and that's something that we will not really cover, but we do want to apply that to the convection problem. And then what I plan to do is talk about the neutral stability curve and look at the types of patterns that one can get. And then summarize something about what is known about their stability. So that's where we're going, this will be what we'll do this lecture, and then in the next lecture, the last lecture, we'll talk about nonlinear stability analysis of patterns. Okay, so let's get started, and I'm going to draw well, actually, what do I want to do? What I really want to do is I want to start off. I want to get to the neutral stability curve, and to do that, I want to talk about the dimensional analysis. So let's just quickly start off by just sketching the type of stability that we might find. So just to recap, the stability criteria that we used was the real part of the eigenvalues of omega as a function of the appropriate wave vector, and I'm going to call that wave vector A. That was the wave vector in the xy plane in the system. So what that tends to look like, something like this. And to make the axes dimensionless, what I'm plotting here is A times D. So A, if you remember, was defined some time ago. Let me just remind you what it is, remind myself. So this was a eigen, well, A was essentially a wave vector in the transverse direction. So let's call this a wave vector. In xy. Okay, so this we'll label these axes like so. And what happens is this: for if you have the Rayleigh number is, let's say, a half the critical one, you get a curve like this. So this is omega as a function of wave number when it is about stable. So this is basically marginally stable here. So this is stable. And then the unstable one would be a curve like this. So that's the situation. It depends on the Rayleigh number. It also depends on this other number, the Prandtl number, which is nu over kappa. And in this particular case, I've drawn it for nu over kappa equals 1. So nu and kappa both come in the denominator of the stability criterion. If you increase nu, then it creates more viscous drag, and so the blobs don't rise. If you increase the thermal conductivity, then the heat just diffuses away. And so the ratio of these two factors that make it harder for convection to occur, that ratio is called the Prandtl number. Okay, so that's one of the ways that we think about the stability. Now let's try to understand how we can reduce the complexity of the parameter space. So the next thing that we want to do is we want to reduce the number of parameters that we need to consider for the phase diagram. Okay, so we're going to do that, and I want to start off by mentioning the Boussinesq approximation that we're making. So this is an approximation that we're going to make, and that is simply this. When we write down the Navier-Stokes equations, we wrote down rho by dt plus u dot grad u is equal to minus grad p plus rho g plus del squared u. So that was our Navier-Stokes equations, and the density was temperature dependent. And that was due to the thermal expansion coefficient. And so the Boussinesq approximation is we're going to ignore the temperature dependence here. And it's an approximation, but it turns out to be a good one, and it makes the analysis much simpler. Okay, so let's now write down our equations as we have them in fully dimensional form. Dimensional form of the equations for Rayleigh-Benard convection in the Boussinesq approximation. Okay, so I'm just going to write down the same equations I have above. And then putting in the expansion coefficient, that's rho bar g 1 minus alpha t minus t bar, and that's all in the z hat direction. And then I have the equation of incompressibility. And then I have the heat equation, du by dt plus u dot grad acting on T is equal to kappa del squared T. And this extra term in the diffusion equation is advection. That's the name for it. And you can see that it couples the temperature and the velocity field. So the velocity field impacts the temperature field, and then the temperature field impacts the velocity field because it enters into the equation for the velocity. And so that's why these equations are very complicated, because there are these feedback effects between these two variables. Okay, so now let's talk about dimensional analysis. So I know you've done this many times in the past. You learned it on your mother's knee, but let's do it in a little bit of a more systematic way. So what is the basic idea? So the basic idea is to reduce the parameter space of the problem. And that can be very useful because it can show how the problem at one scale can be related to the problem at another scale. So this is useful because it can allow us to relate different versions of a problem at different scales. And you've all experienced this because you've all flown in an airplane, and so as an example of why this is useful is that if I want to design an airplane, I want to test it out to see if it works. Well, it's very expensive and so on to build a huge airplane and fly it through air, but it turns out you can make a model airplane, maybe this big, and fly it through a different fluid. And because of the scaling of size and density, you can match it so that the behavior of the model at this scale in one particular fluid behaves like the full scale system in a different fluid, say in air. And so aerodynamic engineers and fluid mechanicians design cars, ships, boats, and presumably the wonderful helicopter on Mars using these similar these scaling ideas. So the example is airplane, car, helicopter design using scale models. Okay, so that's why it's useful. So there's another thing which is mistaken for dimensional analysis. So sometimes people mistake a dimensional analysis as including looking at limiting behavior. So you might have as a variable the size of your apparatus divided by, say, the radius of the Earth. You might say, well, the radius of the Earth is huge compared to the size of my experimental apparatus, so I can just set that variable equal to 0. And I'm going to say a bit more about that kind of use of dimensional analysis a little bit later. Okay, so let's say what is the fundamental statement of dimensional analysis. So the fundamental statement of it is that a dimensionless function cannot depend on dimensionful quantities. So that's a basic statement, and in fact, it can only depend on dimensionless quantities. So let's take as an example the following physics problem. So we may have a problem where we have variables x1, x2, up to xm, and some quantity x, which is a function of those. So we would say x is some function of x1, x2, up to xn. Okay, so that would be the usual setup. Now, so here we're just writing things down as what things depend upon each other, but what we do is we now try to identify dimensionless groups of variables and these are made up of combinations of the x's. So I'm going to call those variables pi. So I'm going to write them like this. So pi will be x1 to the alpha 1, x2 to the alpha 2, x3 to the alpha 3. I'm going to just try to turn my messages off here. So that. And all the way up to x to the xm. And then for x itself, I'll add another variable, x to the power beta. So that might be one variable that we'll call pi. And then I may have other variables. So for example, pi1, I'll write that as x1 to the power alpha 1, 1, x2 to the power alpha 1, 2, x3 to the power alpha 1, 3, etc., all the way up to xm. But now this one does not have x in it itself, and the same thing for pi2. And now the variable is called alpha 2, 1, and so on. Okay, so I can obviously do that. And how many of these are there? Well, the whole point about dimensional analysis is that there may only be n of these. So let's say that the number of these is n equations from these dimensionless groups, but we started off with n. So we have m variables, and in fact only n dimensionless combinations. And so what dimensional analysis tells us is that the dimensionless variable pi must be some function of the dimensionless variables pi1, pi2, pi3, up to pi n, where n is less than n. And this is all that dimensional analysis tells you. And the formal justification of this is known as Buckingham's pi theorem. And it kind of tells you, how many dimensionless groups one has. And there's no unique way to construct them. and you can see why that's true, because the pi's are dimensionless. So I can equally well define pi1 to be pi1 times pi2, and so I can always find other ways to write these variables which are dimensionless. So, but often there's a physically motivated way to do that. Okay, so that's this. Now, the one surprising thing that I've told you is that this is actually a theorem, and in fact it's related to some kind of group theory, and I'm not going to go into the details of that. This was written down in Physical Review 1914, and so it really took a while for these ideas to be formalized. Okay, so that's what dimensional analysis is, and sometimes just this is already useful. But there's the second step is the one that everybody likes to use, and that is you might say for some physical reason one of these variables might be very small. So let's say, for example, that pi1 is very much less than 1. And you know that because there's some physical reason for why you should have that asymptotic limit. And so then what you would tend to say is that pi then is in fact a function not of all these variables, but pi1 replaced by its value 0, and then pi2 up to pi n. And so why this is nice is because now I've only got n minus 1 variables to worry about. So it looks like this, and of course then there's a correction term here, which is going to be of order pi1. And so that's the usual thing, that most of the problems that you've been taught in physics are in this category. And when this is true, this is sometimes known as when the limit as pi1 goes to 0 of f of pi1, pi2, this actually exists and is f of 0, pi2, and so on. This is known as intermediate asymptotics of the first kind. Or complete similarity. So there's no reason for this limit to actually exist. So in many problems, this limiting process doesn't exist. So for example, you might have that the dependence on pi1 might be, let's say, pi1 to some power alpha 1 times some new function g that just depends on pi2 up to pi n. So let's suppose that alpha 1 were positive, then that means that this limit as pi1 goes to 0 of f is actually just going to go to 0, which is absolutely no use at all. Similarly, if alpha were negative, then that would mean that the limit as pi1 goes to 0 of f is going to be infinity. It's going to diverge. Again, completely useless. So those limiting processes don't exist, and so the best that one can say is that in asymptopia, asymptotic limit as pi1 goes to 0, f goes like pi1 to this power alpha 1 times some new function like that, and one simply can't set pi1 equal to 0. And this class of problems is called incomplete similarity. Or intermediate asymptotics of the second kind. So you might say, well, that's all well and good, but why do we care about problems like that? Well, this class of problems includes second order phase transitions. And it also includes many problems in electromagnetism, mechanics, quantum mechanics, etc., etc. In fact, incomplete similarity is more the rule than the exception. So if that limiting process doesn't exist, then what actually happens? So typically in these cases, the statement is that this function pi, this object that we want to understand, in the limit as pi1 goes to 0, has the following functional form. So it might well have pi1 going to some power alpha, and then we'll have this function g that I wrote down. But in fact, it doesn't necessarily have to depend just on pi2. It could depend on pi1 to an exponent, which we'll call beta1, pi3 to some exponent pi1 to the beta 2, and so on and so forth. So this would be the most general form if you have this sort of power law behavior here. And these exponents, alpha, beta 1, beta 2, beta 3, up to beta n, cannot be determined by dimensional analysis. And why? Well, in the form of the problem that we already stated, in terms of the pi's, everything is dimensionless. So dimensional analysis cannot possibly compute these exponents. So in order to compute these exponents, you actually have to solve the problem. So you have to understand the problem, at least in the asymptotic limit. Now, in the problem of second order phase transitions, the analog to the equation in the middle of the page here is the scaling laws for, say, the free energy or the magnetization. So let me just give you an example. So example in thermodynamics or statistical mechanics, let's say. So what you might have is the magnetization of a magnet is a function of the temperature and the external field. and that may have the following functional form. So I'm going to write T is the temperature minus the critical temperature over Tc. So this might go like some constant m0, which has the dimensions of magnetization, times minus T to the power beta times some function of h over T to the power delta. And that would be an example of this intermediate asymptotics of the second kind. This example here is then just the scaling law for the magnetization in terms of the external field H and the reduced temperature. And there's nothing that says in general in statistical mechanics that it has to have this particular functional form. So the point is that this functional form is observed only very close to the critical point. So this is true asymptotically as T goes to 0 and H goes to 0. And so now you can see that there's some kind of connection between statistical mechanics and the theory of asymptotic analysis. And in fact, there's an absolutely deep connection, and in fact, one of the things that we were able to show was that all of asymptotic analysis and in particular singular perturbation theory which includes boundary layer theory, multiple scales analysis, WKB analysis, matched asymptotic expansions. All of these things are special cases of the renormalization group. So all of these things are unified by the renormalization group. So the idea that renormalization group is something that is just restricted to quantum field theory and statistical mechanics is completely wrong. It applies to ordinary differential equations, partial differential equations, and many any of these mathematical physics tools. So the renormalization group is really something separate from the statistical thermodynamics. And those of you who are interested, you can look in chapter 10 of my book for some introduction to that. And then there's a whole suite of papers that we wrote about 20 or 30 years ago that explain how one can use these things in real problems. Okay, so that's something that some of you may be interested in. What I want to do now is I want to return to the problem at hand, which is convection, and I want to apply dimensional analysis to the Boussinesq approximation. Okay, so next up, so I'm going to define my dimensions variables in the following way. So I'm going to just simply take the variables that the thing depends upon, which we've seen what they are, and I'm going to write down some dimensionless groups. So let me do that. So now a bar over a variable will denote the dimensionless form of the variable O, or the operator O, whatever it is. So I claim that these are some good dimensionless variables. So T is a d squared over kappa, that's of dimensions time. So we'll say that in units of T bar. We'll scale space by the spacing between the plate. So we'll call it X bar. We'll scale the velocity field by the thermal conductivity over the plate spacing. That gives you a normalized velocity field. We'll scale temperature by the following: nu kappa over rho bar g alpha d cubed times some dimensionless temperature, which we'll call T bar. And lastly, we'll scale the pressure in terms of rho bar nu kappa over d squared times the dimensionless pressure, which we'll call P bar. So this is something, it's easy to check. So I suggest that you verify that. I'm sure you'll take it as given. So the next thing that we need to do is once we know this, we now need to substitute these variables into the differential equations. So we substitute into differential equations, and I claim this is what you get. And again, this is something that you need to check. So let me write it out. Everything, as you can see, has a bar in it. Okay, so it gets a bit tedious to keep writing these bars, and so we're going to drop them from now on. So this is the Rayleigh number, and the Prandtl number is nu over kappa. Okay, so let's just make sure that everybody understands this from now on. We're going to work in dimensionless variables. And we're going to drop the bars. Okay, So the Rayleigh number that tells you the driving force. And then the Prandtl number tells you about the relative strength of the dissipative mechanisms. Okay, so now we only have two numbers that we need to worry about, the Rayleigh number and the Prandtl number. Okay, so now let's take a look at the qualitative picture of the phase diagram. So what we're going to do in this section is we're going to construct from omega of Q, we're going to construct the neutral stability curve. And then from that, we're going to look at what are some of the pattern forming states. So let's do that. So the first thing we're going to do is plot the neutral stability curve in the following way. So I'm going to draw my axes. So my axes now are the Rayleigh number up here, and Q up here, and what I'm going to do is I'm going to assume that I've done stability analysis. So from the stability analysis, I'm going to assume that I've computed omega of Q as a function of the control parameter. So I'll call that R. And then what we're going to define is the neutral stability curve. And that's the locus of points where the real part of omega of Q and then the control parameter R of Q is equal to 0. So this is the idea, and the R that satisfies this, we're going to call this Rn. So this is the R value. Rn satisfies this equation. And N means neutral. So R, when I'm writing this down, what I'm thinking of is that this is the control parameter. And for us, R is just the Rayleigh number at fixed Prandtl. Okay, so what does this curve look like? So let me draw it for you. So it looks like this. It comes in something like that. And of course, it has a minimum. And so that means that there's a minimum value here, like so. And this value is the critical value, RC. So what does this curve tell? What it tells you is that if you are in the parameter range, so for values of Q and the control parameter R that are less than the stability curve Rn of Q, less than the neutral stability curve. So this is the curve of R equals Rn. of Q. So if you're less than that, that means that the fluid is linearly stable. And so we can say that over here, the fluid is these values, it's stable, and then above those values, it is unstable. So we can then read off from this neutral stability curve the smallest value of the control parameter where instability first occurs. And we can see that this happens at some critical wave number, which I'll call QC. Okay, so now the question is, well, if you have that, what does it become? What does the uniform state become unstable to? So the question we want to understand is if the uniform state is unstable, what does it eventually become once the nonlinearities have restabilized the system? So that's a question that's hard to answer. You'd have to do nonlinear stability analysis. You'd have to solve steady state equations in the nonlinear regime. You might have to do a numerical simulation. So in general, it's hard to answer. It means you have to do some work. But in this particular case, we can write down some typical examples. So let's now write down some simple nonlinear steady states. These are not uniform. Okay, so let's start off with the first one, and the first one is stripes. In convection, people call them rolls. In solid state physics, if you're interested in, say, the electron fluid inside a strongly correlated system, such as a high temperature superconductor, you can have this kind of instability happen as well. Typically, it can happen through a piles instability or other types of instability, and these patterns were called stripes. In liquid crystals, they arise. They're called smectic phases, and so on and so forth. So we'll just use the term stripe. And so let me give you an example. So the velocity field of the system has the following functional form. So it's A times some function that depends on the wave vector Q in the Z direction times a modulation in the X direction that looks like that. So it's a modulation in the X direction with a wave number QC, so we're close to the critical point, and then in the so this is how it varies in space in the x direction, and in the z direction, it varies according to whatever this function uq is. So that would be an example of stripes in the system. So if you look down on this from above, you would see these roll patterns in the x direction. Okay, so here's another one. Squares. Okay, so you might have the following. U as a function of x, it would be a times u q in the z direction, and then you may have the following: e to the I qc x plus e to the I qc y plus complex conjugate. So now I've got one wave going in the x direction, one wave or stripes going in the modulated in the y direction, and so those will form squares. I can have a pattern which looks like an orthorhombic state. So an example of this would be the function u of x is equal to a times some function in the z direction, and then the angle between these stripes is not necessarily 90 degrees. So this would look like the following: e to the I qc x cosine theta plus y sine theta plus e to the I qc x cosine theta minus y sine theta plus the complex conjugate. Okay, so I'm not going to draw these things. I think they're fairly obvious. And I can rewrite the orthorhombic one in the following way. I can write it as a times the q in the z direction, or not in the z direction, but as a function of z, times 4 cosine q1 of x cosine q2 of y, where q1 is qc cosine theta, and q2 is qc sine theta. And then I can do hexagons. This is where I'm going to stop drawing them. So hexagons, which are actually an important case. So you can have that, but you can also have in here another term plus a uq of z times this e to the I phi 3, some arbitrary phase, plus I qc of y plus the complex conjugate. So this is a hexagon, and the variable phi 3 can either be 0 or pi. So that's just basically a sort of phase shift for the hexagons. But anyway, many other states can be constructed. Okay, so these are all possible states. And now the question you might ask is, well, which of these states would actually be observed? And so that, of course, is the question of stability. So the next question is, which of these states and the answer is that if a state is unstable, will not be observed because it will decay into something else. So what that means is that now if we want to understand the patterns, we need to understand the linear stability of these spatial states. And so we use the term spatially extended or spatially non-uniform states. So if I've got, say, a stripe phase, so the velocity field is varying sinusoidally in the x direction, and it's just a constant in the y direction, and it has some direction in the some z dependence. That we now have to work out the linear stability operator about that steady state, and that means that the linear stability operator will not be a differential equation or a differential operator with constant coefficients. It will have periodic coefficients, and so you'll have to then do what's known mathematically as flow K analysis, looking at the stability analysis of differential equations with periodic states. And so that gets very complicated, and so this type of analysis is called, or these instabilities of the patterns are called secondary instabilities. So why? Well, it's basically this. You start off with a uniform state that has the first instability to forming a pattern, and that pattern has another instability to forming a different pattern. And I'm going to leave open the idea that it may not even be a static pattern, it might be a dynamical state, for example, turbulence. So this would be the first instability, and this would be the second instability. Okay, so let's now talk about how one, in principle, does this kind of secondary instability analysis. So let's suppose that we started off with a uniform state, and then we formed a pattern. So we'll call the first instability the primary instability of a uniform state. To a pattern. I'll write that pattern as UQ. It has a wave number Q, and I'll write this function as UQ of x perpendicular and z, where x perpendicular is just x and y. So this is exactly what we have in the z direction. So usually what happens in the z direction. So this is coordinate system, like so. So usually the pattern in the z direction is trivial, maybe just a velocity field. It has some profile like that. But the actual pattern itself is occurring in the XY plane. I'm drawing over here. And so we're interested in the pattern in the X transverse coordinate pattern. Okay, so that's the setup. So what we're going to do is now we're going to assume that U is equal to the steady state, and now we're going to make a perturbation. So we're going to say that U is equal to this UQ plus some delta U, and I'm going to write this delta U, this perturbation, in the following way. So it's going to be a function U1 of X perpendicular and the z direction, and then it's going to be modulated by a wave vector in the xy plane. So I'm going to write that as Q, capital Q, dot X perpendicular, and then it's going to grow with some rate omega, which is now going to depend on the omega of Q, and omega is also going to be a function of big Q times T. So let's just make crystal clear that we know what these things are. So the little q is the wave vector of the pattern. And then the capital Q is the wave vector of the perturbation. And so now we have to compute this omega now as a function of the two Qs. Okay, so you can really start to see that this thing gets quite complicated real quick. So the basic state. So now this is going to be, look, for those of you who've done band structure theory in solid state physics, this is actually going to look very similar. Band structure theory is basically an example of Fouquet analysis. So basically, the basic state is what's called is periodic, and so all we need to do is consider the first Brouwer zone. So example, and I'm going to, of course, try to make this as easy as possible. In the one-dimensional stripe pattern, then the Brouwer zone is Q over 2 is less than the perturbation wave vector in the x direction times Q over 2, like so. So that's the first Brouwer zone. That's where we have to consider the stability analysis. Okay, so now let's ask what can actually happen. Now one can actually do these calculations, but I'm not going to do them for you. So many possibilities can happen. So you could, for example, have, in fact, that Q is equal to 0. You could have that Q is on the zone boundary. And you could have the absolute value of Q is much less than the absolute value of the pattern. So in other words, you're looking at a long wavelength perturbation. Or you could have something like Q is incommensurate with little q. So there's all sorts of things. And if you really want to understand this in exhaustive detail, then there's a beautiful review article, essentially a book, in Reviews of Modern Physics by Mike Cross and Pierre Hohenberg in 1993. So I want to just end this lecture by just showing you some of the examples that are known. So we're nearly done. So let me now talk about what you actually see when you do these calculations. So I'm going to draw an example here. So here's our control parameter. Here is little q, and I'm going to draw the neutral stability curve like this. This is going to be the neutral stability. Like so. And so then from knowing the neutral stability curve, I can read off what RC is, and therefore I can read off the critical wave number QC. So everything below this curve is the uniform state is linearly stable. So let's just say that the uniform is stable below here. Above this curve, the uniform state is unstable, and it's unstable towards a pattern with wave number q, depending on R. Now I'm going to draw for you the secondary instabilities. So the secondary instabilities for this particular problem, the convection problem, look something like this. So in this regime in the middle here you have a stable pattern. So if you're in that range in control parameter, the Rayleigh number and Q, you will have a pattern that is stable. So outside of that, inside this area here and this area here, the periodic state is unstable. The periodic pattern is unstable. Okay, now there's two stability boundaries that you can see here. There's one stability boundary, which is to the left, and that one is called the zigzag instability. And this one on the right is called the Eckhouse instability. It's named after Mr. Eckhouse. There wasn't any Mr. Zigzag. And this thing in the middle, this stable pattern has a name as well. This thing is called the Busse balloon, after Mr. Busse, who calculated this computationally many years ago. So that's called the Busse balloon. Okay, so that's the picture. of the system. Now, well, at least that's the phase diagram. What do these things actually look like? So let me just conclude by writing that. So what I want to end with is the common instabilities of stripe patterns. Ordering with a vector, a wave vector, in the x direction. So the Eckhouse instability that occurs when Qy is equal to 0 and Qx is much less than little qx. And so what does that look like? So if you draw it out, it looks like this. I'm probably going to mess it up, but let me do my best. Okay, so these things are meant to be stripes. So this is the x direction. So these things are meant to be stripes. And what you can see is that the spacing between them has varied in the x direction. So this is a period changing instability. So that's the Eckhouse instability. The other one I want to draw for you, excuse me. The other one I want to draw for you is the zigzag instability. So the zigzag instability. So in that one, Qx is equal to 0, but Qy is much less than Qx. So it has a pattern in the y direction, which has a wavelength which is larger than the spacing between the stripes. So what is that going to look like? If I draw the pattern, it's going to look something like this. So these are the stripes. And so on and so forth. Okay, and so that is the a zigzag instability, and it turns out that the shape of the stability boundaries, and for the zigzag one, turns out to have a linear shape. That's this linear dependence I've drawn over here on the left-hand side. The Eckhouse one has a parabolic shape, and you can only determine that by a detailed calculation. Okay, so that's where I'm going to end today's lecture. And next lecture, we will start talking about the pattern formation and how they emerge beyond linear stability analysis. So we're going to learn how to do nonlinear analysis of patterns. And what we're going to see is that the description that we end up with looks just like the Ginzburg-Landau theory for superconductors and phase transitions and so on and so forth. Okay, so that's the end of today's lecture.